Alright, so this is chapter 6. This is a new unit. Unit 3 is a pretty big unit. It's called field theory. Chapter 6 will be gravitational fields. Chapter 7, electric fields. And chapter 8, magnetic fields. To break this unit down a little bit, we're going to have a little test after chapter 6. And chapter 7 and 8 together will be a larger test, because electric fields and magnetic fields, as we'll learn later, are really two sides of the same coin. So today we're going to start with orbits and Kepler's laws. But first, let's talk a little bit what a field is. I think I've mentioned it before. So a force field is not something you would see on Star Trek, right? Instead, they exist all around us, and different force fields interact with different properties. For example, all around us there's a gravitational field. Okay, and this is provided by the Earth, right? Right here in this space in front of me where I'm pointing, there's a certain value for the gravitational field right there. So there's a field that exists right there that interact with objects, as we learned in chapter 3 with Newtonian universal gravitation, objects that have mass. So if I take an object that has mass and put it inside a gravitational field, then it will interact with that field and feel a force. Okay, gravity is a little bit more complicated than that, as we will see in this chapter, but it's important to understand what a field is when we start. So, move on. We did the universal law of gravitation. This was chapter 3. We're all good with that. But what we're going to do right now is we are going to go back in time a little bit. So Newtonian came out with the universal law of gravitations, and then about 100 years later, Henry Cavendish experimentally calculated that proportionality constant G. Okay, now how he did that was with something called a torsion balance. So there's a picture of it here. Let me move my face. Okay, so here's your torsion, and then here's a long rod with small masses on the end. Then you place larger masses close to them, and that gravitational attraction wants to rotate that rod. But just like a spring, the more a spring gets stretched, the more it wants to pull back. In this case, the torsion, the more it twists, the more it wants to untwist. And so eventually it'll twist to a point where it reaches sort of an equilibrium, where the forces are balancing that force of wanting to untwist and the gravitational force. And you can use those measurements, which Lord Cavendish did, to calculate G. But I said we're going back in time, so let's travel, sorry, my jokes, back in time a bit. We've already done that. Here we go. All right. So we all started with, you probably know this already, but Ptolemy, who said that the Earth is in the center. Okay, it was an incorrect assumption, but looking at his model, and this is the model he created, it's actually quite impressive. Right? You have the moon orbiting the Earth, the sun orbits the Earth. Now Mercury and Venus rotate around nothing, and they keep in line with the sun as they rotate around like this. And then you have the outer planets going around, rotating around nothing, but also in their own orbits. Now, we know today this is wrong, but it's a model, and it was a model that was used to correctly locate these planets in the sky, these wandering stars. Later came Copernicus, who said, I have a simpler model. If you just put the sun in the center and order the planets like this, each orbiting the sun, and of course the moon orbits us, then you can also make the same predictions. And it's a very accurate model, and it's a lot simpler. Unfortunately, he didn't have proof. Now, technically, Ptolemy didn't have proof either, but he was supported by the church for many centuries. Where Copernicus, on the other hand, was not supported because he did not say the Earth was the center. So he ended up getting burned at the stake, unfortunately. It wasn't until Galileo came along with his spyglass or telescope, and he was the first person that actually pointed up at the stars. And he actually gathered evidence to prove Copernicus's model true. Okay, well, that's one story. But here's someone else that you probably haven't heard of, Tycho Brahe. He was one of the last naked-eye astronomers, meaning he didn't use a telescope. And he was very meticulous, so he had very, very, very good data regarding all the objects in the sky, because he constantly followed them, right? Wrote where they are and when in the sky they were. He was also really, really stuck up, so he actually challenged someone to a duel and got half of his nose cut off. But we're not going to talk too much about him. We're going to talk about his student, Johann Kepler. And upon dying, Tycho Brahe left all of his data to Johann Kepler. Now this is still before Newton. Johann Kepler is still before Newton, and he used Brahe's data to actually come up with 3 laws of planetary motion. And those are the 3 laws we're going to go over. First law. Each planet moves around the sun in an orbit that is an ellipse. So he used data, experimental data, to prove that it's an ellipse, right? Of course, it was later that people wanted a mathematical law that showed that it's an ellipse, and that's when Newton came out with his universal law of gravitation to say that the force is inversely proportional to the distance, right? And so what Newton did was really took Kepler's laws of the universe and the laws that govern motion here on Earth and combined them to say that they're one and the same, which is why Newton is so famous. So his first law says they orbit in ellipses. Now you haven't done the mathematics for ellipses, and you won't in high school, but just to give you a brief overview, if you have a circle, okay, a circle will have an object at the center, right? Not necessarily an object, but it will have a center. An ellipse won't have a center. What it has is 2 foci. Here's one, and here's the other. And Kepler's first law said that at one of those foci is the sun. There's nothing at the other, but the sun exists at one of those focal points. Okay. Next law. Kepler's second law. The straight line joining a planet and the sun sweeps out equal areas in space in equal time intervals. Yeah, right? Let me explain what this means. So look at this picture. Let's say we have a planet, take Mars. Let's say Mars is orbiting, and as it gets to here, I hope you can see my mouse as I'm moving it, as it gets to here, we start recording, say time. Let's say we record 1 month. Exactly 1 month later, my mouse is gone there. Exactly 1 month later, it's traveled here. Okay? And then what we do is we sweep out this area, and let's just call it area 1. Okay, at some later point in its orbit, we do the same thing. Right over here, we start timing. We finish timing exactly 1 month over here. And that sweeps out another area. Okay, let's call that area 2. What Kepler's second law says is that area 1 equals area 2. And what that means, what that actually means is when you're further away, you're actually moving more slowly than you are closer up. This also explains why we don't see comets for such a long periods of time, because a comet will come very close to the sun, swoop by it, and we'll see it in the sky for a short period of time, and then it goes off into deep, deep, deep space. Okay, way past the orbit of even Neptune. And as it's all the way away, far away, where we can't see it anymore, it's moving very, very slowly. And it won't come back for maybe a couple hundred years, depending on the comet. Okay. This we went over in chapter 3, we set Newton's law of universal gravitation equal to centripetal force, and we came up with an equation for orbital velocity. Now this is for a perfect circle, but even still you can see that the velocity is somewhat inversely proportional to the radius, meaning the greater the radius, the slower the speed. Okay. Kepler's third law, again, it's very wordy. The cube of the average radius r of a planet's orbit is directly proportional to the square of the period t. Mathematically, right, we say r cubed is proportional to t squared. And we can set that equal to an equation if we have a proportionality constant, and this is Kepler's constant c. That's very, very important. Kepler's constant c is not a universal constant. It is different depending upon your orbit. So what do I mean by that? I mean, if you have a satellite orbiting the Earth, right, you will have a certain Kepler's constant. If you have the moon orbiting the Earth, or a Tesla car orbiting the Earth, right, you will have a certain constant c, and it will be the same for all of them. But if you have a moon orbiting Mars, now we're orbiting a different object. The value of c is different. You will have a value of c for each object that you're orbiting. There's one for the sun, there's one for every planet. Whenever something is orbiting something else, right, that object you're orbiting has a certain Kepler's constant. Okay. Now what we're going to do is we're going to put a couple things together. So I'm going to take our orbital velocity, and for a perfect circle, and I know we did say planets orbit in ellipses, but other than Pluto, right, planets are very, very, very circular. In fact, you can look this up online. I don't have the information for you, but when you're orbiting in an... Okay, so I actually went and looked up the values for you because this is interesting. So when you orbit in an ellipse, you have a certain eccentricity value. If your eccentricity is 0, then you're a perfect circle. So a circle really is a very special case of an ellipse. Okay, so if you look at the planets, and this will say the object and their eccentricity, Earth is 0.016. If you were to have a computer draw the shape of the orbit that the Earth goes around the sun, you would say it's a circle. You would not be able to recognize it as being an ellipse. It looks so perfectly circular. Right? Same with the other planets, Uranus, Jupiter, Saturn, the moon around Earth, Mars. Okay, the ones that start getting a little bit high are Mercury, which is 0.2, and Pluto is somewhere around here. We'll ignore Pluto, it's not a planet anyways. So Mercury is the one orbit you can probably identify as being elliptical, not perfectly circular. Whereas all the other ones, you can assume them to be fairly circular. Unless, of course, you want to try and shoot a rocket over there. Then you probably want to be more exact. But for most cases, yeah, we can assume that to be a perfect circle. So let's go back to my PowerPoint. There we go. So here's what we're doing. We're looking at the orbital velocity. And if it is a perfect circle, we can simply say the period, or the time it takes to go around once, is distance over speed, where distance is the circumference of that orbit. And if we put these two equations together, we get this equation. If we square both sides to get rid of that ugly square root, we get this. And then we'll notice we have a t squared, and this r squared over this gm over r will give us an r cubed. So we have a t squared and an r cubed. So let's rearrange that, right, so that we actually have r cubed over t squared. Well, if we go back to Kepler's third law, r cubed over t squared equals Kepler's constant, capital C. And therefore we have a way of calculating what Kepler's constant would be for any orbiting body if we simply know the mass of that body, because it would equal gm over 4 pi squared. So that's Kepler's third law. So let's do an example. This is example number 2 on the back. I'll have you try one on your own. It's more qualitative. And question 2 says the average radius of orbit of Earth about the Sun is 1.492 times 10 to the 8 kilometers. We're going to have to change that into meters, so it will be times 10 to the 11 meters. And the period of revolution is 365.24 days. Determine the constant c. Okay, so we're going to use Kepler's third law. It's not too hard. It's actually quite simple. Let me make this bigger. Okay, what I find that most people make mistakes on in this chapter is simply plugging in the big numbers on their calculator. It's easy to make a mistake with such huge numbers on your calculator, and you're about to see why. So we can calculate the constant, and I'm going to write subscript s because it's for the Sun. And it's our radius of Earth cubed over its period squared. Now the radius is, what was it, 1.492 times 10 to the 11 meters, and we have to cube that. See what I mean about big numbers? It's going to get worse, because period, we need to be in seconds. So it's 365.24 days. We're going to multiply that by 24 hours in a day, multiply that by 60 minutes in an hour, multiply that by 60 seconds in a minute. That will give us how many seconds. But we also have to square it. See where the mistakes can come in? So try this on your calculator. You should get the same answer as me. All right, 3.335 times 10 to the 18 meters cubed per second squared. What do those units mean? It's a proportionality constant. That's it. All right, so that's part A. Part B says an asteroid has a period of revolution around the Sun of 8.1 times 10 to the 7 seconds. What is the average radius of its orbit? Okay. Well, in this case, we know what c is. I just erased it. But we're going to redo this for the asteroid. Now the value of c will be the same because the asteroid's orbiting the Sun, which was what the Earth was orbiting as well. And it's telling us what the period is, so we just need to rearrange this equation to solve for its radius, which will be the cubic root of cs times period squared. Yeah, more big numbers. Okay, so we got this to be 3.335 times 10 to the 18, and they give us the period, which is 8.1 times 10 to the 7, and we have to square that. And then we take the cubic root of all that, and we'll get 2.799 times 10 to the 8, or 10 to the 11 meters, or 10 to the 8 kilometers, if we put it back into kilometers. Okay, so that's it for that lesson. Tomorrow we're going to talk about gravitational potential energy, but we're not going to talk about it on the Earth. We're going to go up into orbit.